Hi everyone, this is Manish Nath from Hex-Star Universe, and I'm going to be your host for today's session. First of all, I want to thank everyone for taking their time to join us today. So, today is the first day of our World Space Week celebration. I hope every one of you already know what World Space Week is. But for those of you who don't know, World Space Week is an annual holiday observed from October 4th to October 10th in over 95 nations throughout the world. World Space Week is officially defined as an international celebration of science and technology and their contribution for the betterment of the human condition. So, on the first day of the World Space Week, we have today organized a live session on binary stars. And today, to enlighten us on this topic, we have none other than Mr. Teja Begari with us. He is an official ambassador at AAVSO and an awardee of Global Kids Achievers Award for the category of astronomy. We are really glad to have him here with us today. So without wasting any more time, I'd like to request Teja to proceed with today's session. Thank you, everyone.
Thank you so much for having me here. I'm really glad to present today about one of the really interesting topics, at least for me, which are the binary stars. I would just like to present my presentation. All right, so binary stars, as was mentioned, this is Teja Begari. I'm an ambassador for the American Association of Variable Star Observers, an international organization which basically coordinates variable star observations and has been doing that for more than 100 years now. So, binary stars, they're the topics I would like to cover today, which are binary stars. What exactly are binary stars? Second one is the types of binary stars. While I explain about one of those types of binary stars, I would like to show NAPLABs, uh, these are those kind of software. This is one of those software which basically helps us to understand about quite different topics in astronomy with really wonderful presentations and simulations. So I also wanted to take you through the NAP labs. And the formation of binary stars is what we're going to end up with. So starting with what are binary stars? Binary stars, as the name suggests, are physical pairs which describe around the orbits about a common center of gravity because both of the stars or both of the bodies have mutual gravitational attraction. Here, if you observe, I specified the term physical because physical here means there is a gravitational attraction between both the bodies. That is what physical is what I meant. But why did I specify that? Is because there are binary stars called as optical double stars, which are not exactly binary stars, but as seen from Earth, we see two stars to orbit each other, which are not really orbiting each other, but we see them to be orbiting each other relative to Earth. So that is the reason why I specified physical pairs because I'm not talking about optical double stars, but I'm talking about physically attracted binary stars. So this is how something the binary star would look like. So this is from the universe today. The first, there is a big star, which is a primary star, which is more brighter. And then we have a small star, which is called a secondary star, which is fainter. The primary star is also called a parental star. So I hope this is an introduction to what exactly these binary stars are. So we have different types of binary stars depending on quite many things. And the main types of binary stars are visual binaries, spectroscopic binaries, and eclipsing binaries. So I would like to start up with visual binaries, the first one. So visual binaries is a binary star system in which the component of stars can be described individually and can be resolved by looking at a telescope. And once we make long-term observations, we can plot the relative positions of each star in the system. So let's have a clear explanation of how we see binary stars from Earth. So, because binary stars are quite far from people on the Earth, we see them to be a single star, as seen from Earth. We see them to be a single star, and even if we, uh, find any kind of change, we see the change to be in a single star form, basically. So let's take an example of algal, which is an eclipsing binary, which is also a variable star. So when we take algal, we see that there is a change in its brightness. But then once we look at algal from Earth, we see to be a single star, and we see a change in its brightness as a single star, but not as a binary star. But we can do it once we look at it from the telescope, so which is going to be a visual binary. So uh, visual boundaries are really recognized by their wide separation in the orbits. So generally, the motion of the fainter star about its brighter components observed, and the apparent relative brightness of the fainter and also the primary star can be traced out. So if they first find out the complete luminosity of that particular system, and then once they find out the relative motion of the secondary star, they find out the luminosity of the secondary star, and then subtract it from the complete star's luminosity, and that's how one can trace out the brightness of both primary star and secondary star. So there is a process which scientists use to determine the orbit of the visual binary by observation. So what is first done is the angular separation. So angular separation is basically measured in arcseconds, and then the position, that is the direction of the fainter star relative to the brighter one. Say a fainter star is going towards uh, a different angle to the brighter star, and that is how a position is observed of the fainter star. And this direction is measured by the angle which basically will subtend the line joining the two stars with north and south line, which basically means the east to west, right? So this is basically a brief of uh, the process one uses to determine the relative orbit of visual binaries. So I wanted to take an example of a visual binary star, which is Sirius, which is quite a really famous star because it is the brightest star in the night sky. So Sirius, also called the dog star, is a visual binary, but many people think that it is a single star, but it is a visual binary. Sirius was discovered by F.W. Bessel in 1834. F.W. Bessel was also the first person who actually predicted that Sirius could be a binary star, and also was the first person to discover it. So Sirius is, as said, is the brightest star in the night sky. The primary star is so bright that the secondary star is almost invisible. And later, R.G. Aitken calculated the elements of the orbits in 1918, and then they were confirmed by different people. One of them was a Wallet who obtained the exact, almost the same results. So the period of evolution was observed to be 49.5 years, and the maximum angular separation was 11.2 arc seconds, and the minimum angular separation is 0.2 arc seconds. So, uh, can you not hear me well? Is there a
So we can hear you, sir.
okay? Great, thank you. So yeah, I hope this would really help. Okay, so the period was found to be 49.5. Just a minute. I'm sorry, just a minute. I'm sorry. Just a minute. Let me go back to the presentation. All right. So yeah, this is about Sirius, the visual binary star. So here are the pictures of the two scientists, F.W. Bessel and R.J. Aitken. I'm sorry, I did not mention the credits. Both of these are from Wikipedia. So yeah. And now talking about spectroscopic boundaries. Visual binaries are not quite famous. The reason is most of the binary systems are are either too far to be resolved using current telescopes, or are very close that can be resolved separately. So it's not like we cannot, there's no proper way at least to measure those which are not too far or not too close. So then how can we determine or detect such type of binary stars? We use spectroscopy, which is basically the language of stars. So the majority of binary stars have been discovered by Doppler shifts in the spectral lines. So as we know that there are about 50% of stars in the galaxy are known to be binary stars. So those stars which have been discovered using Doppler shifts are called as spectroscopic binaries. So how do we do it basically? So if a binary star is unresolved into its components, then the spectrum, whatever we get, will be the combination of both the primary star and the secondary star. So both the combination of both the spectrums, both the stars spectrum will be there in one single spectrum. So as these stars, because they orbit each other, we can assume them to be moving towards us and moving away from us. So let's say a star A may be moving towards us, and a star B might be moving away from us. So if a spectrum, the spectrum of A, because it is moving towards us, will be blue shifted with higher frequencies, which means it will have shorter wavelengths. And B probably will be moving away from us, and it will be red shifted because it is moving away from us. That's what we know. And if stars are moving across the straight line of sight, then there would not be any kind of Doppler shift. So the lines stay in the proper mean positions. So as the stars continue orbiting, A will reside to its spectral lines, will be moving towards us at the end, at the red end of the spectrum, and B will move towards the blue because they will be orbiting each other, and over due period of time, the change in the spectrum will be seen. So there is this really beautiful illustration given by the Australian Telescope National Facility, where you can actually uh, really observe. See, there is the star B and star A. Because it's on the line of sight, we basically do not see any kind of uh, Doppler shift. And here, the star B is moving away from us, and star A is moving towards us. So it's quite obvious that A is blue shifted because it's moving towards us, and B is red shifted because it's moving away from us. And getting back over here, you see the stars are in line of sight. Even here, the stars are in the similar line of sight. So you basically see no Doppler shift. So it would be quite hard for scientists to detect that kind of binary stars. But then, because these binary stars will always be moving, so we will quite have spectrum seen if we concentrate on that particular star system over a long period of time. And coming to here, we have A, which is again moving away from us, so it will be red shifted, and B is moving towards us, it will be blue shifted. Again, coming back, we have both of these in the line of sight, there will be no Doppler shift. So I've taken this picture from the Australian Telescope National Facility. It's really well easy for one to understand how scientists basically determine if that particular star system is a binary star or not. So a spectroscopic binary system, I'll just read out the one given by the Australian Telescope National Facility, just so you know. Uh, High mass star A and lower mass star B. We are assuming that A is the primary star here and B is the secondary star here. A, which is also called as a peripheral star, orbit around a common center of mass, common center of gravity, and the observed combined spectrum shows the periodic splitting and shifting of the spectral lines, as we can see here. Yeah, I hope you already had a look at the change in its the change in its spectrum, right? So, uh, and the amount of shift is a function of the alignment of the system relative to us and the orbital speed of each of the here it is given as stars, but then it can be measured, it can be resolved into single star, and even that is a really very good way to be done. So these kind of stars are the spectroscopic binary stars, which are determined using the spectrum. Now we have another type of binary stars called the eclipsing binary stars. So eclipsing binary stars are uh, are a special kind of spectroscopic binary stars. Ecliptic binaries are kind of my favorite binary stars because they're also variable stars. They change their brightness. So here I also gave the magnitude and the time in days. Most of the time it's also taken in Julian date, at least at the VSO. So here an ecliptic binary is a special type of spectroscopic binary. So whenever these stars orbit each other, there is an eclipse formed. As I always mention, that eclipse is basically what we mean is we deal with the shadows. But then eclipse here in star systems is basically a change in the brightness of the complete star system. So I wanted to show you the binary stars instead of a presentation. I wanted to show it to you in NAP labs, which are now I'll be going through. First, let me go through eclipse and binaries, and then show you each and every section of NAP lab. All right. So basically, introducing NAP labs. The NAP labs are also abbreviate to Nebraska Astronomy Applet Project, which basically provide a computer-based lab targeting uh, undergraduate introductory astronomy audience, but then anyone can use it, and it is free. So let me go to the Eclipse and Binary Simulator here. So it right. So here, if you can change the longitude, you also have to check at the normalized visual flux, where there is a you can see the graph, because of which you will know that there is a change in its brightness. So let me go to let me change some of its mass, increase radius. Temperature really doesn't matter as of now with this particular. All right. So now if you start the animation, it basically shows you how the eclipsing binaries are rotating, and also if there is a change. Look, now because yeah, here, because both of these stars are moving towards us and away from us, there will be a spectral shift. There will be a Doppler shift we see. But because this simulator is not showing a spectroscopic binary and is going towards the ecliptic binary, it does not show the spectral lines. But then this is where you basically know. And now, whenever these stars come through a line of sight, let us wait for it to, come through the line of sight. Right. So over here,
Please tell
uh,
the full form of NAPLAN.
sorry.
You have talked about the labs. So the full form of NAP labs. NAP.
Yeah, I mentioned that it's going to be the Nebraska Astronomy Applet project. I'll share the link with you uh, in the group chat. I mean, in the meet chat once we're done with it. So here, let us assume that these stars are spectroscopic binaries. Forget that these are ecliptic binaries. Forget the chart, and think that these are spectroscopic binaries. And because these stars are in a single uh, line of sight towards us, we do not see any kind of change. So earlier, as I showed, over here you can see some change because the star in blue is going away from us and the star in red is coming towards us. So the star in blue will basically get red shifted, and the star in red will be getting blue shifted. I mean, it's a bit confusing when I name it to be blue and red, but then assume them to be like that. All right. So this is how we can go through eclipsing binaries. It can really help one to understand how eclipsing binary goes. You can always change your mass, radius, temperature, and you can always enjoy doing it. I would like to go to. I would like to show you a little bit of NAP labs. So the first one we have here is a solar system model, which basically explains to you both geocentric model and heliocentric model. Uh, Look, so the one Ptolemy gave, you can always have a look at this. And then we also have the heliocentric model, which shows the planetary configuration simulator. There are also it also gives you quite really amazing information about different models, and also about um, you know about whatever it is explaining. So it is quite really an amazing lab. So I just wanted to show you each and every one of these, just so you know. And there is also this basic coordinates and seasons. So there is also the season ecliptic simulator. It's literally so good that you can know how and where the Earth is. So let's go to October 4th. Look, so it really gives you a wonderful, uh, you know, the simulation of each and everything. So over time, you can actually go through it completely and see how it, uh, right. So over there, there is, yeah. So you can always be doing it. And not just these, but then in basic coordinates and seasons, there are even more, you know, sections which have been divided. And then we have the rotating sky, which shows the sidereal time and an hour angle demo. And we have motions of the sun. We have lunar phases, planetary orbits, black body curves, and UVB filters, hydrogen energy levels, HR diagram, eclipsing binaries, the ones which are shown, atmospheric retention, exoplanets, variable star photometry, the cosmic distance ladder, and habitable zones. So all of these are really well explained in the NAP labs. So I would really suggest you to go through it. I'll be sharing the link of the NAP labs in the group chat, in the meet chat, so that you will, if you're interested, you can always go install them in your computers. All right. So I think eclipsing boundaries are quite clear with the NAP labs, because uh, I always show eclipsing boundaries with the NAP labs because it is quite easy for one to understand. All right. Now going through the formation of binary stars. How do you think binary stars could be formed? How exactly these stars might have come closer to each other? Is it even possible? So, since about 50% of all detectable stars in the uh, galaxy belong to the binary systems, many theories have been introduced about the formation of binary stars over since the ages. So, the first theory was the capture theory in the year 1867. John Stoney, this person, proposed the capture theory of the formation of binary stars. So, what exactly capture theory says is it's quite simple. It says that the two independent stars approach together and they start revolving around each other due to gravitational attraction. But then the capture theory is not really accepted by many scientists, because the phenomena of two stars getting close to each other is very unusual in the history of galaxy, because the stars will be rotating over the central bulge of any galaxy, and then they will be in their own motions, and the stars getting closer to each other is not something we basically it's not usual. So the capture theory was rejected by quite many scientists. So capture theory is not the actual theory which explains. The Macmillan's theory of binary star formation. The Macmillan theory is quite interesting, but then it is also not true. Let's find out why. So, according to the Macmillan's theory of binary star formation, binary stars will be formed from planetary systems. So, as we know that the planets and the star systems will basically be moving through the interstellar medium, and in this process, they accumulate interstellar material and they grow in mass. So, some amount of mass gained by the star is re-ejected, but the planet basically stores all the material, which basically means this planet will be growing in its mass, right? Due to this, planet gains more mass than that of the primary star, the the base the star which the planet is revolving around. And then it is quite obvious that the gravitational force increases, and the distance between them decreases, and this leads to the formation of a faint star, which means the large planet is now formed into a faint star. So the other planets will either be absorbed by the primary star or by the large star, which is now the secondary star, which is the faint star. And according to this theory, this is how close binary stars will be formed. But why is Macular's theory of binary star formation not true? Because uh, the mass of the faint star must always be less than the primary star. But the observed mass ratio in the binary star is not less than half, which basically is quite against to Macular's theory. So it basically says that Macular's theory of binary star formation is also false. Now, getting to the true theory, I mean, at least the theory which is quite satisfactory, is the fission theory. So the fission theory can possibly explain all the aspects of the origin of binary stars. So the fission theory basically says that when a gaseous body is rotating slowly, it takes up oblate spheroidal shape, and for a body as such, it has a tendency to concentrate mass at the center with a corresponding rotational speed. So there will be a gaseous bulge in the center, and whenever this gaseous bulge is rotating slowly, it starts dividing up into two parts, and which ends up being, you know, at the two ends of the star, there ends up being a star with two different equal masses, but there'll be two stars. This is the fission theory, which is given by James Jeans. So the fission theory is one of those theories which is quite satisfactory to all the astrophysicists. So as of now, fission theory is the one which scientists think is true. But then there can be always new theories that come up, and new theories can always come, and we quite can know if there is a change in over due to time, if we try to find out if there is a change in the theory, or if it disproves any kind of basic theory of physics, or if it disproves any kind of thermodynamics, fluids, or basically gases, because the fission theory itself is not a theory taken by the James himself, but it was a theory given by a few other scientists, but it was not applied to stars exactly, but it was applied to compact gaseous states. So that is what Sir James Jeans applied to the fission to stars. So uh, this is how we can go through it. So yeah, I wanted to complete my presentation first and then get back to NAP labs. So now we can actually go through the motion of sun. So here we have the motion of sun simulator, so which literally shows you, and also you can change on which part of the earth you are. Say we're here in India, so let me keep it there, and you can always change the animation speed. Let me keep it over here, and you can always, you know, have your time. You can keep the time. So let's say it's 10. All right, and then it's October 4th, right? And you can start the animation. You can see how basically the sun moves today and in the night, and then it gets to the next day where it shows you uh, how how it how it starts over. You can continue doing this forever, literally forever, because uh, you see, you can start on the 1st of January, and you can pause at any particular time, and you can know where the sun is. So let me go through it a little more. Okay, let the sun come to So at this particular point of day, say it's 9:44, you can see that the observer's latitude is 12 degrees north. So you can always have each and every um, you know details given on specific day, whatever you're observing, and you can always relate it to the night sky or the day as we're talking. And then after we're done with motions of the sun, let's go to planetary orbits. It basically shows you a clear understanding of Kepler's laws. You can change the semi-major axis. The eccentricity can be changed. You can change the planet. Let's go to Jupiter or probably Earth, right? And you can see how there is a change. But what if you create your own hypothetical planet with an eccentricity of, let's say, it is zero eccentricity, exact circle, and then you basically change its semi-major axis, the astronomical units, and you can always calculate your radius, and you can keep on empty focus, show center, semi-major axis, and semi-minor axis, both of these. So it basically gives you a clear understanding of Kepler's laws of planetary motion, and you can always, you see, it's basically very clear understanding about the Kepler's laws, start sweeping and start sweeping. So here both of these are going to be equal, this part and also this part. You will be understanding it really well if you have the eccentricity, right? And as you can see, so this area and this area is going to be equal as the Kepler's second law say. So you can really enjoy the Kepler's laws if you go through the NAP labs. And then we have lunar phases. Here it's quite similar to the sun, but here we're dealing with the moon. We have black body curves, hydrogen energy levels. I wanted to go to some interesting ones. So yeah, over here you can know of where a star is going to be pointed out. I mean, in a HR diagram, Hertzsprung Russell's diagram, you can know where a star is going to be if it has these temperature and luminosity compared to that of the sun. So it's always really great to go check the HR diagram. With you can create your own star with your own you know uh, temperature, luminosity, the size, and all. And I showed you eclipsing binaries. There's also extra solar planets, exoplanets basically. Right. So how do we? I just wanted to give you this because we are dealing with eclipsing binaries. We did. So the same way how we detect eclipsing binaries, that's the exact same way how we also detect exoplanets. So if a star, right. So there is an exoplanet between in front of a star, and then you can always check if there is a change in its uh, uh, right. As it will be moving, you will be seeing a change in its light curve. So light curves really help us to uh, just a minute, I'm just unable to move the. All right, so here as it is down, I mean as it is here, there's no change, there's no transit, you basically see. So the line is just straight. And then if you go a little bit, get back to it. All right. I hope you did observe that there is a change in its light curve. It happens only when the planet is in front of the star. So the exoplanet simulator is also there, and there's the exoplanet radial velocity simulator. We have variable star photometry. I quite did show this a lot of times, so let me not go there. And we have the cosmic distance ladder. You can always go through all of these. It not just shows you simulations, but also gives you a really well explanation of all of these. And the habitable zones, where you can explore the habitable zones in the Milky Way. And you see here if there is any particular or not. So if the initial mass of the star is 0.30, then the habitable zone is going to be somewhere here. And the initial planet distance, say if it is, yeah, so if it is 0.338 AU for the mass of the star 0.30, then the habitable zone is not going to be 0.510 AU or between that. So you see how wonderfully they have been created and the habitable zone, right? So here this is something really good about the NAP labs. Right away, let me share the NAP labs uh, link in the group chat. So with that, thank you all. I hope you all have clear skies. If there are any questions, I would really love to take them.
Thank you, Teja, for this wonderful presentation and also to enlighten us on this topic of binary stars. Now, participants, if you have any questions, you can turn on your mic and ask Teja directly, or also you can write in the chat and we will read out the questions for you.
Can a star hold more than 3 to 4 stars? Because I have heard triple star systems. So is it possible that a star system holding more than 4 or 5 stars in their system?
Well, it completely depends. Even I did hear about multiple star systems where there are quite many stars which orbit a common center of gravity. But then the theory of explanation of the triple star system is again a problem because how do you exactly know that these triple star systems have been formed? Uh, so yeah, it definitely can be possible, but then the explanation, as far as my knowledge, is not really given out correctly because even with the binary star systems, we do not have a concrete explanation. But the fission theory is something which uh, satisfies quite many uh, answers to different questions. So yes.
Okay.
Hello, sir.
Atharva, yeah, sure. Go on.
Sir, is there any problem with the habitable zone in the binary star system? Sir, you're on mute, please. You're in
Right, so
mute.
that's a really nice question. There can be a habitable zone for a binary star system, yes, but then the planet needs to be quite far from the binary star because there is a lot of light and you know a lot of light and heat produced by both the stars, and if possible, the planet basically needs to orbit the center of mass of which both the stars are orbiting and should not overlap in the orbits of both the stars. If that happens, the planet no longer is going to be there, right? So it definitely can be possible, but then the planet definitely needs to be quite far from uh, the the binary star system.
Sir, if the binary stars can explode as the two stars get more heat?
Sorry, your question wasn't clear.
Sir, when the two binary stars are near, can they explode in space?
You okay? You're asking, can the binary stars explode if they are
Yes,
near?
sir.
Oh, right. This is technically possible. Wait, it is definitely is concretely possible because we have these stars called as cataclysmic binaries. So what basically happens with cataclysmic binaries is that there's a big star and there's a small star, a primary star and a fainter star, and the end stages of the life cycle of both of these stars. Say the big star went supernova, or let's say it's a red giant, and then there's a small star which became a white dwarf, right? White dwarf stars are really dense and also really take in all the material. So while this basically happens, the material from the primary star is literally sucked in by the white dwarf, and which creates a cataclysmic variable again. So this is again a variable star. So here, whenever this happens, if both the stars somehow manage to go a red dwarf, and if one star is not a white dwarf, both of these stars can go a supernova. Yes.
Okay, so Atharva Patil have asked, can you explain about the three-body problem?
Which three body problem are you referring to?
Atharva, it would be great if you can clarify.
Oh,
Okay,
the
so
trajectory of 3 stars. Right. It really isn't like a problem, but hypothetically, it definitely is possible. Um, so, like, can you explain your exact question? Because three bodies can be possible. Because let's talk about in the sense of asteroids, taking to a really small level of understanding. So there are asteroids which are triple asteroid systems. These are possible because they move around the common center of gravity. They revolve around a common center of gravity. So a triple asteroid system is possible. I think we can relate this to stars because uh, stars with similar masses uh, to relative to other stars, and talking about asteroids with the mass that asteroids have, when this basically is possible because of the gravitational attraction, I believe triple star system would also be possible because, well, it's the same thing. It's still gravity. So I definitely think it definitely would be possible.
so
Uh,
DK sir, can you please ask your question? You have raised hand. So
just a minute, just a minute. I lost one. Yeah, please
I
go
want to
ahead.
ask, which is the first binary star have discovered? Because as you show in the PPT, Sirius has discovered in 1834, but when I googled, then it shows something different.
Right. So discovery of the first binary star has been from a quite long time. Since we have had telescopes, discovery of binary stars has been for a quite long time. But what I meant about Sirius is that it was I took the example of Sirius because Sirius is the brightest star in the night sky. That's the reason only why I took Sirius. But else I could take quite many different stars. I could have taken quite many stars which are of my own interest or of quite famous. But then Sirius was one of those stars which have been discovered. Uh, Sirius was there. They knew Sirius, but then they discovered it to be a binary star because of its brightness. And Bessel was one of those first persons who said that, who basically first predicted it that it could be a binary star. And later on, it was confirmed that it was a binary star by observations of Rowlett, who was one of those persons who observed binary stars, uh, specifically Sirius. So yeah.
Sir, can you
so
share the link of that map labs, please?
Oh sure, I forgot. I will share it right away.
okay, so DK sir have asked, sir, in binary star system, do both stars revolve around each other, or one big star remains stable and the smallest smaller star revolve around the bigger one?
Just a minute, let me share the NAP labs.
Yeah, sure.
Sir, this is my question.
Where is the NAP? Okay, all of you have are in touch with the Hex-Star Universe Gmail, right? So I think I'll share it to them, and then they can share it to you. Or okay, let me share it now. Okay, there we go. I'm sharing it in the chat. So that's the link of the binary star. Okay, in the binary star system, the both stars revolve. Yes, both stars revolve around each other. But then if you take the theory of Macmillan, then possibly both stars might not revolve around each other till they form binary stars. You see, we should always consider each and everyone's theory, even though they're wrong, but we can just have, we can think about it. So yeah, the both stars revolve around each other, yes. And also, I believe someone was asking about Aladdin. I also would like to share the link of Aladdin. For those who do not know about Aladdin, you can always go check the tutorials. Aladdin Sky. It's a tool which really helps you to uh, There we go. That's the link of Aladdin. I can also show you how Aladdin works probably in the next minute if possible.
So if anyone else have any other questions, please feel free to ask your
I have
questions.
question
I have a
regarding.
question.
Yeah, sure. So first, Sriloki, ask your question, then Atharva, you can ask you.
Actually, I have heard about the HD limit, Humphrey's Davidson limit, and Earendel star has not fitted with this concept. So as we know that astronomers need to redefine the definition of HD limit. So are other stars fit in this category? Hello.
Oh, right. So, did you ask any question? I could not hear you well. You're talking about.
I was talking about the HD limit, Humphrey's Davidson limit. Earendel star is not fitted inside this category. As we heard, the astronomers need to redefine the definition of HD limits. So other stars fitted inside this category, like Sirius or any more, or only this is an exceptional case.
I'm still not sure what you're asking because the background noise also. Can you please write it?
Okay, actually there is a noise in the background, so just a minute.
Uh, how can we connect with you, Teja?
Oh, right. This also run on mobile. I don't think that will be on mobile, Tushar. I don't think it's going to be run on mobile. Arta was asking something.
Yeah, Teja. I wanted to know if we could connect with you on any platform.
Could you please repeat? I think I have a problem with.
It's a sextuple star.
Yeah. So in Gemini, I kind of did observe Pholex a few times, but then it always is one of those stars uh, which kind of shows availability. So I did observe Pholex a few times. So I would be really happy to talk about it. All right. So talking about the Pholex star system, right?
Yes.
Hello. I was
Yes,
talking
please.
about the Earendel star, which has a greater luminosity
Ah.
as you compare to the HD limit. So what is
Hmm.
the exactly HD limit?
I think Teja is having some network issue, but we're trying to fix that.
Good morning, Amit ji, and everyone.
Good morning, sir. Sir, is the session complete?
Teja is having some network issues, so he's trying to reconnect. So it would be great if you keep your patience for a little bit of time.
Yes, sir.
Okay, we're really sorry. Teja lost his connection and couldn't join today again. And so I think we have to end our session here for today. Also, if you want to connect with him, you can connect with his email ID that is provided here. So first of all, I want to thank everyone for joining us today and making this session a successful one. So and also to celebrate the World Space Week from 4th of October to 10th of October, we have organized live sessions throughout the week with different topics and different speakers on different topics. So don't forget to subscribe to our YouTube channel and follow us there, and watch our other live sessions too throughout the week. And I think with that, we have to end our session here for today.
Thank you, sir. Thank you for the session.
Okay, no issues.
Namaskar, good morning.
Thank you very much.
Thank you everyone for joining us here today.
Thank you for the session, sir.
We'll be ending our session today.
I think tomorrow Amit Raka's talk,
Yes,
na?
yes. Tomorrow, Amit sir will be here with us today with a new topic. Thank you.
Okay. We'll be waiting for that session.
Thank you, sir.
Sure. Thank you everyone.
Thank you very much.